Good afternoon. Welcome to this second session. Tuesday, in our first session, we looked at some preliminary issues associated with numerical computation. Then we went on and tried to find out how to fit data, interpolate, extrapolate data, and also take numerical derivative and to numerically integrate given data. This is all things that we did in the last session. So today's session we are going to spend exclusively on some linear algebra concepts, and if you have any questions or queries related to the first session, we can take them also. Today we will find some time when we can have question and answer sessions. If you have some questions related to what was done earlier and also questions related to what I am going to do today. Okay. So today's lecture will consist of the following. Okay, so we will have a short introduction. Then we will look at the first application of linear algebra, which is related to coordinate transformations. Okay, so this is a very important thing and we keep doing it all the time. So we need to understand what coordinate transformations are and how it is done mathematically. The second problem that all of you might be very familiar with is eigenvalues and eigenvectors. So I want to show a few examples of uses of eigenvalues and eigenvectors in understanding some of the issues in material science and engineering. While we look at eigenvalue, eigenvectors, we will also look at some methods like fixed point iteration and Newton's method and bisection method, etc., which are basically methods for finding zeros of a given polynomial. Okay. But they are also useful to get the eigenvalues of a given matrix. So we will look at some of these methods, and there is also a method called power method. So we will look at all of them, and this is with specific reference to getting eigenvalues and eigenvectors. And finally, we will look at solution of simultaneous linear equations. They are very important and they arise in very many different contexts. So last time when we were discussing fitting, I was talking about nonlinear fitting. So we will take a look at an example of that and how you have to solve simultaneously certain equations to get solutions for those kind of problems. And we will discuss methods like Gaussian elimination or Gauss-Seidel algorithm, iterative algorithm for solving simultaneous linear equations. Okay. And we will also discuss what is known as a design matrix. Again, that is related to fitting. When you have to fit to some functional form which is not a polynomial form, then this kind of design matrix becomes very useful. So today we are going to discuss all this over the next couple of hours. Okay, so matrix calculations or what is known as linear algebra is very useful. So there are many times that you have been taught in engineering mathematics, lots of linear algebra, matrix algebra and things like that. And we will find 2 or 3 cases where these are very useful. First is in affecting coordinate transformation. Second one is like I said, eigenvalues and eigenvectors. Finally, solving simultaneous linear equations. Let us consider any material. An example I have taken here is polycrystalline copper. Polycrystalline because we know that crystals like metals like copper or gold, etc., have a crystal structure, and the crystal structure is defined by the unit cell. So the crystalline unit cell, how it is aligned with respect to the laboratory frame of reference or external frame of reference, that then decides what is the orientation of the crystal. Most of the engineering materials, metals and alloys, are polycrystalline. That means in that material, if you go to different parts of the material, the unit cells will be aligned differently with respect to a reference frame of reference, which could be the external or laboratory frame of reference. So let us take the example of a copper polycrystal, and these crystallites which are oriented differently are known as grains. So let us consider 2 adjacent grains in polycrystalline copper. Let's call them as A and B. This means you go to some sample and some region of this copper sample, you will find that there are unit cells which are aligned in a particular fashion with respect to the external frame of reference. That will be considered as one grain. And if you move away from that region, there will be another region where they are aligned but differently than in A. So those are known as B region. So we have two adjacent grains. And the base vectors that define the unit cells in A and B, let them be given by AI and BI. Because this is a three-dimensional structure, AI will have A1, A2, A3, BI similarly will have B1, B2, B3. But the lattice parameter, because this is the same copper, so it is the same in both crystals, okay, both crystallites as they call, or grains as they are called, they will have the same lattice parameter because it is the same copper material. Only thing is the two orientations, if one is aligned with say its 100 direction aligning along with the x-axis of the laboratory frame of reference, the other one might be aligned with say 1, 2, 3 direction aligned with x-axis, or both might have some arbitrary HKL or UVW aligned with the x-axis of the external frame of reference. Okay, but the lattice parameter is not going to change because it is the same material. It is the crystals of the same material. Only their geometry, their three-dimensional orientation is different. Okay. So let us further assume that the grains are oriented such that the x-axis in both the cases, the A1 and B1 in the grains A and B are parallel to each other. Okay. So they are aligned. Let B2 make an angle of 30 degrees with A2. So that is, you can think of it as aligning the x-axis and making an angle of 30 degrees along the y-axis for you to go from A to B. And similarly, B3 makes an angle of 30 degrees with A3. So you now have orientation. So one is A1, A2, A3. B1 is aligned with A1. But B2 and B3 each make 30 degrees with A2 and A3 respectively. Now, if you have a vector R which has components 1, 2, root 2 and 2 in the AI frame of reference, we want to know what are its coordinates in the BI frame of reference. So, these kind of computations become very important because we might have different grains, and sometimes these could even be different crystal structures. For example, the A and B could be different lattice parameters, for example. So many different possibilities are there, but we will consider the simplest case where both have the same lattice parameter, but the orientation of one with respect to other is different. So now I have a vector. The important thing to realize is that the vector has its own independent existence. Okay. A vector is a quantity which lives in a three-dimensional space because it has a magnitude and it has a specific direction. But when we refer to it, we want to give some coordinates for this vector, and those components or coordinates of the vector depends on what is your frame of reference. Okay, so the simplest thing that you can think of is that if I draw a line on the board or the corner of the board, suppose if I want to say what are its coordinates, so I can give some 2, 3 numbers. But those numbers will be different depending on where my origin is. For example, if the corner of the board itself is the origin, then it will get a vector which is 0, 0, 0. That is the 0 vector or null vector. But if suppose one corner of the room is taken as the origin, in the other direction there is no, say in the z direction it will have no value, so that will still remain as 0, but x, y values will depend on, suppose the board is fixed, say it's on 10 feet along the wall and at a height of say 5 feet, then 10, 5, 0 will be the coordinate, but we are referring to the same point, we are referring to the same vector. Okay, so but it can take different components depending on where the origin is. Now this is a very simple case. The origin just got shifted. There was no other change that has happened. But you can think of more general changes. It could be rotated. It could be even shrunk or expanded. So all sorts of possibilities are there. But we are now considering a case where I have a vector. Its components are given in one frame of reference, that is the A frame of reference, in which it has 1, 2, root 2 and 2 as the components. And now I want to find out what will its coordinates be if I am using the B frame of reference to refer to the same vector. Okay, so that is what we want to understand. Okay, so to describe what the components of the R vector are going to be in the B frame of reference, we need to define what is known as a rotation matrix. Okay, so what is a rotation matrix? That is what is shown in this slide. So because the x-axis remains unchanged, so the A1 versus B1, so that makes 0 degrees, so that is 1, and A1 B2 and A1 B3, they are the same because they are not changing. With respect to B1, the A2, A3 will have the same angle as A1 because A1 and B1 remains to be the same. However, A2 makes an angle of 30 degrees with B2, and A3 makes an angle of 30 degrees with B3. So which is what we said it's doing. Okay, A3 makes an angle of 30 degrees with B3, and similarly B2 makes an angle of 30 with A2 and 60 degrees with A3. Okay, so that is what is shown. So it is cos 30, cos 60, and this is cos 120 and cos 30 because of the geometry. Okay, so if this is A2 B3 is making 60, B3 A2 will be making 120. So, and these can be written as 1 0 0 0 cos 30, cos 60 is cos 90 minus 30, cos 120 is cos 90 plus 30, and cos 30. Okay, of course then you can simplify using some trigonometric identities. So the matrix that describes the coordinate transformation from AI to BI is 1 0 0 0 cos 30 sin 30, 0 minus sin 30 cos 30. Okay, so sometimes you would have seen this. So rotation matrix is defined with respect to the axis about which you are rotating. It will have just 1 and zeros, and depending on the angle by which you rotate, you will get cos theta sin theta minus sin theta cos theta. So this explains how that comes about. So this is the rotation matrix. Now I know that in A the components of the vector is 1, 2, root 2 and 2. I know that this is the rotation matrix which tells how to go from A to B. So if I take this rotation matrix and if I multiply it with the vector which is used to describe the components of the vector in the A frame of reference, then I will get the new vector, which is how it will be represented in the B frame of reference. Okay, so you multiply, you know, cos 30 sin 30 minus sin 30 cos 30 values, and you will get these numbers as the components of the vector in BI frame of reference. So coordinate transformations of this type is done very regularly in lots of materials problems. Many a times there is more than just coordinate transformation that has to be carried out. For example, you might have a thin film. The film might be grown in a particular orientation. Then you will have all the property tensors associated with the film. For example, strain or stress or elastic modulus or any other property that you can think of. If they are tensor properties or tensor quantities like stress, strain and elastic moduli and so on. So to translate them to other frames of reference. For example, you might have grown your crystal along certain orientation. You might want to translate it to some other orientation, which is where the say calculations, elasticity calculations, for example, will be simpler. So you need to do this coordinate transformation from the current frame of reference to the reference frame, or sometimes from the reference frame to the current frame of reference. So these kind of things they are done. And they are done primarily by making the rotation matrix. And what is rotation matrix? So if you have observed, rotation matrix is nothing but the matrix made up of the direction cosines of the AI with BI. Okay, so in other words, so I'm going to show you what is the structure of this rotation matrix. Okay, so if you have an old frame of reference, right, that is like our AI frame of reference, and you have some new frame of reference, so that is like our BI frame of reference. Okay, then the cosine of the angle of this AI versus B, right? So that is the cosine of the angle A1 versus B1, cosine of the angle A1 versus B2, cosine of the angle A1 versus B3. So similarly, cosine of the angle A2 versus B1, cosine of the angle A2 versus B2, cosine of the angle A2 versus B3, and cosine of the angle A3 versus B1, cosine of the angle A3 versus B2, cosine of the angle A3 versus B3. So this matrix is known as rotation matrix. Okay. So as you can see, because these are cosines of the angles, so you know that dot product is A dot B is, for example, mod A mod B cos theta. So you can take A dot B divided by mod A mod B, then that will give you the cosine theta. So you can take the vectors that make up the old frame of reference. So any frame of reference, for example, in 3 dimensions, it will have 3 basis vectors. That is what is required to completely describe the frame of reference. Similarly, you will have some 3 vectors for this frame of reference. You can take the unit vectors, you know, this is B1, B2, B3, and this is A1, A2, A3. So you can take each one of these vectors and look at the direction cosines with these 3, and then you fill them in. So this is how the rotation matrix is made. And if you have the rotation matrix, as you can see, the rotation matrix consists of only direction cosines, and then we use the property from trigonometry that cos 90 plus theta or cos 90 minus theta is having some relationship to sin theta. That is how the regular, I mean the rotation matrices are typically written like this, right? Rotation matrix is 1 0 0 0 cos theta sin theta 0 minus sin theta cos theta. Okay. There are sometimes confusion whether the minus sign is here or here. So it depends on the way the theta is defined, the way the rotation is done. So in all those cases, it's always easier to go to this more basic definition, which is given in terms of the unit vectors of the old frame of reference and unit vectors of the new frame of reference. You can look at the cosine of the angles between them and make this matrix, and this matrix is a rotation matrix, and because this is made up of direction cosines, its determinant will be equal to 1, that you can prove, and its determinant is 1 because it's a rotation matrix. Okay, so the rotation matrix is 1 with determinant of R is equal to 1. Okay, so this determinant is 1 because rotations generally do not produce any strain. It does not change the lengths of vectors. Okay, rotations just leave the vectors unchanged. They just change their orientation, because of which the determinant will always be equal to 1. Okay, so this is the first thing. So let's go back to the slides now. So rotation matrix, this is how you make the rotation matrix, and this is how you deal with vectors and coordinate transformations, etc., using the rotation matrix that you produce. Okay, so this is very simple computation, just some matrix multiplication, which all of you must be familiar with. This first component is 1 because 1 0 0 multiplying this and adding, so 1 into 1 is 1, plus 0 because 0 into 2 root 2 is 0, plus 0, so that becomes 1. Okay, in this case it becomes a 0 cos 30 times root 2 and sin 30 times 2, so that adds up to 3.449. Okay, and in the third case it is minus sin 30 times 2 root 2 plus 2 times cos 30, and that comes to 0.31. You can check these values and confirm that this is the components of the new vector that you get when the transformation is made. Okay, so this is the first example that we are interested in understanding. Okay, so because the rotation is supposed to leave the magnitude of the vector a constant, like I said, the determinant of the rotation matrix is 1. You can also say it the other way. If you have a matrix, its determinant is 1. When it acts on any other vector, it is going to leave its magnitude unchanged. So, if you do a rotation, a pure rotation leaves the magnitude of the vectors on which it is acting unchanged. Okay, so it just changes its orientation. It does not change its length. It does not produce any contraction or expansions for the vector. Okay. Okay. So there is something known as Bain strain, which is very, very important. So what is Bain strain? It is a homogeneous deformation which transforms FCC austenite into BCC martensite. Okay. So why is this important? Steels get some of their very good properties because of this phase called the martensite. And how is the martensite produced? Martensite is produced by heating the steel and quenching it very fast. When you quench it very fast, it doesn't undergo the usual phase transformations that it would undergo. Instead, it produces this martensite phase, and this is not even an equilibrium phase. If you have a phase diagram, you will not see martensite there. So this is a non-equilibrium phase that comes about when you cool the material very fast. So what happens is, when you cool the material, it is not having time to change into the other crystal structure that it would prefer to have, which would reduce its free energy. So thermodynamically, that is the most stable state, but for kinetic reasons it's not able to go there. There is no nucleation, there is no growth. So because of which, when you cool it very fast, then there is this excess carbon that is left, and the material is not able to undergo the transformation that it would like to undergo, which results in the formation of what is known as martensite, and it happens through what is known as a diffusionless transformation. So in material science, we distinguish between civilian transformations, which are like phase transformation, and military transformations, which are like phase transformations of diffusionless type, like martensite formation. Okay, so one of the important things to understand about martensite is its crystallography. Okay, in the crystallographic coordinate system of the FCC phase, so you have an FCC phase which is going to go into a BCC phase, which is the martensitic phase. So the transformation that takes you from FCC to BCC, that strain, which is known as Bain strain, has the representation, but there is a small problem with this slide that I have written. So I'm going to write the matrix in the slides here. Okay. So the Bain strain, okay, let's call it as B. The B matrix has the following representation. It is 1 point, I have written 28, which is wrong, 1, 2, 3, 8, 8, 3, okay, 0, 0, and 0, 1 point, 1, 2, 3, 8, 8, 3, 0, 0, 0, 0 0.7, 9, 4, 7, 0, 5, okay. So this is the matrix that is known as the Bain strain matrix. This represents the homogeneous deformation when you go from FCC to BCC martensite. Okay. So I hope all of you know what is the FCC crystal structure. So it is a cubic structure in which you have atoms at all cube corners as well as face centers. Okay. All the 6 face centers get atoms. What is BCC? BCC is another crystal structure where you have atoms at all cube corners, and then you have one atom at the cube center. So this FCC to BCC transformation, BCC Martensite transformation that happens in steels, that is represented by this Bain strain, and this Bain strain, the exercise for you is to show that it leaves a particular vector. Which vector? Let us call that vector as some R vector. That R vector is given by this -645452 0.408391 0.645452. Okay. Now, what do I want you to do? I want you to show that this deformation leaves this vector undistorted but rotated. Show that acting B on R leaves R undistorted. Okay. In other words, I want you to check that acting B on R rotates the R vector, but it leaves its magnitude unchanged. That is, if this is R, it becomes something like this. So its magnitude is not changed, just that its orientation has changed. So that is what I want you to check. Can you do the calculation and tell me if it is so? And then we will have a chat with one of the classrooms, anyone, whoever volunteers, to understand how this computation has been carried out, how to show that this is going to leave it rotated but undistorted. Okay, so let's take a couple of minutes and do this computation. The problem is to show that the Bain deformation matrix B leaves the vector R, which is shown on the screen, undistorted but rotated. Okay, so please do and let me know. Okay, then if you are able to show that it is undistorted but rotated, please put a note or raise your hand so we can have a chat, and we can also discuss how to solve. One of you, whoever solves, can tell how you solved it. What is the method that you use? How to show that it is undistorted but rotated? What is the property you need to look, and how do you prove that it is undistorted but rotated? So if you are able to solve, please leave a note or raise your hand. If you are having the slides that I sent, there is a small change there. The number is not 1.283883, but it is 1.123883. Okay. So if you use the numbers that is given in the slide, you will get slightly wrong answers. Yeah. PECTN. Are you able to solve? Yeah. Are you able to? Yeah. Okay. So I see some chat message. Some able to. So I see three numbers. So what are these numbers? Column vector. Okay. So the column vectors that number. So I got some answer from PhD-CP. Okay. So the numbers that okay. So the numbers that somebody is reporting is a column vector. Let us call this as y. That is 0.725412053. Okay. 0.458983, then 0.512951. Okay. So how did you get this column vector? How did you get this column vector y? Did everybody get this vector? And if so, how did you get this vector? You can raise your hand or you can write the answer in the chat. Yes, this is the right vector. This is minus 0.7. Okay. Okay, so Shobhan, the TA tells me that there should be a minus sign here. So some of you might want to check. So how do we get this vector? So we have the B vector, right? So B vector is given by this 1.123883, 0.794705. Okay. So I have the other vector R, which is given by this, which is minus 0.645452 and 0.408391, 0.645452. So to show that this Bain matrix rotates this vector, all I need to do is to take the B vector and multiply it by R. That is, I take the B vector and multiply with the R vector. And let me call that as the Y vector. That is what some of you have given, and that is minus 0.72541205 and 0.458983 and 0.512951. So this obviously shows that the vector R has been rotated, because the components that you get here are different from the components that you get here. So if you have some components, the vector has been rotated to some other components. But to show that the vector is undistorted, what we need to do is to show that the magnitude of R, if you subtract the magnitude of Y, it should be equal to 0. If the magnitude of R and magnitude of Y is the same, then we know that R vector just got rotated, that is, its components changed, but its length did not change. So to prove that it is so, all you need to do is to take the magnitude of R vector, magnitude of Y vector, subtract them and show that it is equal to 0. So can you take the magnitude of these two vectors and tell me what is the difference that you get? Calculate the magnitude of this vector, calculate the magnitude of this vector, and take the difference and tell me what is the number you get. Okay, you can write it in the chat or you can raise your hand. You can also make the computation easy by taking just the dot product, because dot product is not going to give you magnitude but magnitude squared, and if the magnitude squared they are the same, then magnitudes are the same, right? So you can also take R dotted with R minus Y dotted with Y, because it gives mod R squared and mod Y squared. So that should be equal to 0. So that is the easier way of showing. You can avoid taking two square roots, and it's a fairly simple computation. Okay. Can you do that and tell me what is the difference that you get? You get exactly 0, or you get some number? You get some number, what is the magnitude of that number? So that is what I'm interested in knowing. Did anybody get the number? So somebody got 0.999 minus 1. Okay. So we are, getting back to, okay. So if the two numbers are the same, okay, if it is not a numerical computation, but if it is an exact analytical computation, you would have obtained 0. But as you can see, the numbers, we are approximating. So the numbers that I have written are only accurate up to some number of decimal points, because of which the computation when you do, you get answers also accurate only up to certain number of decimal points. So it is 0. 0 for all practical purposes, but on the computer you will not get 0. I think the TA Shobhan got something like 1 into 10 power minus 6. Yeah. So the difference when we calculated, we got it to be of the order of 10 power minus 6, but it depends on the accuracy to which you do the calculation. This calculation was done on a computer which was doing double accuracy. So the numbers were accurate up to 10 power minus 15 or something. And in that representation, then when you tried to do, you got this number. But as some of you might have noticed, yes, you do get numbers. Sometimes 0 is not exactly 0 in numerical computation. So this is very, very important to keep in mind. Depending on the accuracy of the numbers that go into your expressions, the accuracy of the numbers that you find here and here, you will get this expression satisfied according to that accuracy. Okay, so it's very important to remember that. So sometimes it is 0, you might not get exactly 0, but that does not mean the computation is wrong. It just means that that is the accuracy to which you are doing the computation. Okay, so let's go back to these slides. We have found that the deformation leaves the vector undistorted but rotated. The next exercise that I want you to do is slightly more involved. It's really not a numerical computation, but it works on the same idea that we have been discussing. What I want you to do is this: to show that any vector x that satisfies this criterion, where eta 1, eta 2, eta 3 are basically the diagonal components of the Bain distortion function. Okay, so that we had, so that's what we saw. And if you have this, here again it is not 1.28 but 1.123883. Okay, so please remember. So are the principal strains of the Bain distortion in the FCC frame of reference. So anything that has this vector form. What is the vector form that we are talking about? It is a matrix. This is eta 1, this is eta 2, this is eta 3, and if so, any vector which satisfies this condition will remain undistorted but will get rotated. Okay, so the exercise is to show that this is so. So how do we show that? It's fairly simple. So you have already seen how we have done the computation. So you have done the numerical calculation. So what I'm going to do is that I'm going to do it analytically. How do I do? Let me take the B matrix, and I said that it consists of eta 1 0 0 0, eta 1 0 0, eta 2 0 0 0, eta 3. Okay, so this is the P matrix. Now let me consider an arbitrary vector A. Okay, let me say that its components are x1, x2, x3. Okay. Now what I want to show is that B vector acting on A leaves A vector rotated but unchanged. Okay. So let me call the vector y as the vector that I get when I act B on the A vector. So what do I get? I act eta 1 0 0 0, eta 2 0 0 0, eta 3, and I act it on x1, x2, x3. So I get the components of y vector as eta 1 x1, eta 2 x2, eta 3 x3. So because now the components of eta A, which is x1, x2, x3, are changed to eta 1 x1, eta 2 x2, eta 3 x3. That means depending on eta 1, eta 2, eta 3 values, the x1, x2, x3 have changed. So if this is positive and large, then that will be expanded. If it is positive and small, then these will be contracted, and if it is negative, it will go in the opposite direction, and so on and so forth. Okay, so the vectors now A and Y have different components. So obviously, even if their magnitudes are the same, they are rotated. Okay. Now to show that their magnitudes are the same, I just need to take the magnitude of this vector and subtract it from the magnitude of this vector. Like I said, I am going to do a still simpler calculation. So I am going to say y dot y minus a dot a should be equal to 0, because square root of this is basically the magnitude. If it is so for the square root, you are going to take the positive value because this is the magnitude of a vector. So you might as well take the square itself and see what happens. So if you now do, this is going to be eta 1 squared x1 squared plus eta 2 squared x2 squared plus eta 3 squared x3 squared minus x1 squared minus x2 squared minus x3 squared equal to 0. So now you can collect all the terms. Okay, let me do it here. Let me collect all the terms with eta 1 x1. So that gives me eta 1 squared minus 1 x1 squared. So these two terms are done. Let me take the next two terms. So plus eta 2 squared minus 1 x2 squared plus the last term, these terms, eta 3 squared minus 1 x3 squared equal to 0. Okay. So let's go back to the slide. This is exactly what I wanted you to prove, and we have proved it. Okay. So what do we get? We see that eta 1 squared minus 1 x1 squared plus eta 2 squared minus 1 x2 squared plus eta 3 squared minus 1 x3 squared equal to 0. So basically the x1 squared plus x2 squared plus x3 squared is the original magnitude. Eta 1 squared x1 squared plus eta 2 squared x2 squared plus eta 3 squared x3 squared is the new magnitude squared. So if the magnitudes are the same, this condition has to be satisfied. So in other words, whenever, for whichever x1, x2, x3 these conditions are satisfied, those vectors will remain undistorted, but they are rotated because their components are now modified by these three numbers eta 1, eta 2, eta 3. Okay, so this is very, very important. Why is this important? Because crystallographically, that there are undistorted planes or undistorted directions play an important role in how the phase transformation itself proceeds. Okay, so that is the reason why these computations are very important. Many times you want to know if there is a direction which is undistorted, if so, what is that direction? And then when you go look at the microstructure, you will actually see telltale signs of these directions participating in the transformation in a particular fashion. Okay, so that is why this is very important. Okay. Now the second kind of problems in which we are interested in are known as eigenvalue problems. Okay, so all of you must have seen eigenvalue problems in some context or another. So here I am going to give you a couple of examples of the use of eigenvalue problems in problems related to material science and engineering. Okay, so it's very important. Many of you might have taken a stress tensor and found out the eigenvalues and eigenvectors. They are called the principal values and principal directions of that stress tensor. So, and that plays an important role. So you have the so-called Moore circle construction, for example, and things like that to identify which are the principal directions and principal values. So what is the importance of principal values and principal directions? They are very special. Okay. They are very special because they lead to some sort of scaling, and the different eigen directions are independent of each other. So even though in a general tensor, when it acts on another vector, all the components might get involved. When you go to the eigenvalue vector in that frame of reference, so you can identify a special frame of reference where the problem gets decoupled. Okay, so that is the reason why we are worried about this kind of principal value, principal direction calculations. The complete determination of all eigenvalues and eigenvectors, if you want to do numerically, then you have to do what is known as a QR decomposition. Okay, but QR decomposition is something that can be carried out on a computer. It's very difficult to carry out a QR decomposition using pen and paper. It's not impossible, but it's very tedious. You need to do lots of computations and lots of things you need to keep track of, and you need to do the algebra properly to get the answers. So I'm not going to discuss QR decomposition, but it's important. Some of the references that I have talked about earlier, like Gerald and Wheatley, for example, has some information on QR decomposition. You can take a look at it. And there are also lots of information online for QR decomposition. Now, one of the online resources which is very good is the numerical recipes textbook, which is available for free for download on the net. So there are details of what QR decomposition is and how it is carried out. But in this module, suppose I restrict myself to methods which are ideal for hand computation. Okay. So we will look at a couple of cases where such important information can be obtained just by doing some hand computation. Okay. So obviously we are going to restrict ourselves to small matrices and finding eigenvalues for such small matrices. Along the way, we will also learn a few numerical algorithms and methodologies which will help us understand them better. So how do we do? So let us consider the description of a general deformation. Okay. What is a general deformation? General deformation is one which consists of both strain and rotation. That is, when you take a body and when you try to produce deformation on it, you might also end up rotating it. Okay. So let us take a look at it. What do I mean by this? So let us take a general body. Okay. Now this body can be stressed, right? I can impose traction, so it will have a shape change. Say, let me squeeze like that. So then probably it becomes something like this. Okay. In addition, after this is done, I can also rotate this body and that might come something like that. Okay. So the transformation, that is, this is strain and this is rotation. These two put together gives me this. Okay. So P is the general deformation in our definition, R is the rotation, okay, and E is the strain. So what we are saying is that our P is given basically by R and E together. Okay. So here E is the pure strain and R is the rigid body rotation. What is a pure strain and why are we interested in the strain? Because pure strain is a strain. Okay, so let's go back to the slides. Pure strain is a strain that is represented as a symmetric matrix irrespective of frame of reference. Okay, so this is one of the properties of strain. Strain is a symmetric matrix. What do we mean by symmetric matrix? Strain is a 3 by 3 matrix. Okay, so strain will have 9 components. Okay. So it will have 1 1 1 2 1 3, 2 1 2 2 2 3, 3 1 3 2 3 3. So it will have 9 components. Now if it is symmetric, then 1 2 and 2 1 component are the same, 1 3 and 3 1 component are the same, 2 3 and 3 2 component are the same. So instead of 9 independent components, you will get 6 independent components. The diagonal components and the say upper diagonal components. All the lower diagonal, off diagonal components will be the same as the upper non-diagonal components. So if you have such a system, that is known as a symmetric matrix, and pure strain is a strain that can be represented as a symmetric matrix, that is irrespective of frame of reference. It doesn't matter which frame of reference you are looking at, it will always give you a symmetric matrix. Okay, and along the principal, in addition, along the principal axis, suppose there are only simple extensions and contractions. So if you can describe it like that, then that is called pure strain. So what is it that we are doing? We are taking a general deformation and we are saying that the general deformation can be split into 2 parts. One is a rotation, other one is a pure strain. Pure strain is one where the strain is symmetric and consists of simple extensions and contractions along the principal axis. Okay. So let us now consider this. So let us take the P, okay, and I said that P is represented as R times E. Okay. So let's try to calculate P transpose P. That will be what? Right? Because P is RE, P transpose P will be RE transpose RE. Okay, so you have to remember when you do the transpose operation, RE transpose in terms of R transpose and E transpose will become E transpose, R transpose, R E. Okay, so this is very important property. Okay, so now R transpose R is going to be I, because that is a rotation matrix, and rotation matrix, for rotation matrix the transpose is basically also the inverse. So that means you have E transpose E. So P transpose P is basically E transpose. Okay. So, and for a pure deformation, you can show that E transpose is nothing but E. So P transpose P becomes E squared. Okay. So this is an identity. So let's go back to the slide. Slide 12 basically shows this identity. So P transpose P is basically equal to E squared. So in other words, what it means is the following. Okay. So let's take a look at, I mean, why is this important, or why are we interested in such computation? So let us consider a particular system, cobalt 6.58% iron alloy. It undergoes a martensitic transformation. Okay. So the first Bain distortion we were talking about, an FCC material undergoing a martensite which has BCC structure. But cobalt 6.58% iron alloy undergoes a martensitic transformation in which it goes from face-centered cubic to hexagonal close-packed structure. Okay. There is no density change associated with this transformation. What does that mean? Okay. If there is no density change associated with the transformation, that means that the volume is not changing, because density is mass per unit volume, and if the structure is undergoing transformation but the density is not changing, that means that volume is not changing, because the same mass remains even after transformation. So if volume remains constant, then the density would remain constant for the material. If volume increases, for example, then the density would come down. If the volume decreases, the density would go up. But because there is no density change, we know that the volume is not changing. Okay. So there is a plane during the transformation which is known as the invariant plane. Okay. And that is the close-packed 111 plane of FCC. Okay. I hope all of you know which is the 111 plane of FCC. Okay. So let us draw a unit cell. Okay. Okay, because this is FCC. Right. So that is FCC. Which is the 111 plane? So it is the plane that is bounded by these three body diagonals. What are the body diagonals? So on this face there is a body diagonal, on the bottom face there is a body diagonal, and on the back face there is a body diagonal. So if these three put together, that is, if you take the x, y and z directions, which are the A, B and C directions of the crystal, right? So one unit length along A, one unit length along B, one unit length along C. If there is a plane that intersects at these 3 points, that is the 111 plane of FCC. Okay, so invariant plane and there is a shear direction. Shear direction is 1 1 bar 2, and the magnitude of shear is 1 by root 8. Okay, so how do you get 1 1 bar 2? So you need to take 1 unit along x, 1 unit along y, and half a unit along z, but not in positive z direction, in the negative z direction. So that is basically the vector. So it has components along this is 1, along that is 1, along this is half. So some vector like that. So in that direction, that is the shear direction, if you give a shear of 1 by root 8. Okay, so now why or how this is important? This is important because, so let's go back to this slide. So the invariant plane is a plane which remains unchanged when the transformation takes place. So in this alloy, you are going from face centered cubic to hexagonal closed packed, but one particular plane remains as it is in both the crystal structures. Okay, so that is known as invariant plane, and that invariant plane happens to be the 1 1 1 closed packed plane. And if you consider that, and if you consider a shear of magnitude 1 by root 8 along 1 1 bar 2 in the FCC direction, that is what the resultant martensitic structure is all about. So this is the crystallographic information that we have. Okay. Now given this information, so what do we know? We know that the density does not change, which means that there is no volume change, but there is a particular plane which remains undistorted, and overall transformation can be understood as a shear of a particular magnitude along a particular direction. So this is the information that we have about the transformation. Now if this information is given, and then you are asked the following information. So what is the information? So we want to know what is the maximum strain experienced by any lattice vector of the FCC lattice as a result of this transformation. Okay, so sometimes we are interested in questions like this. So we have a cobalt 6.58% iron alloy. It is in FCC state. You can make it undergo a phase transformation to a HCP state. When you do that, there is an undistorted plane, that is the 1 1 1 plane of the FCC. And the transformation itself is understood to be a shear of magnitude 1 by root 8 along the direction of FCC. Okay, so this is the information we have. And during the transformation, there is no volume change. Okay, so and problems of this type with all this important material science information are described in great detail in a textbook which is available for free again online by Badeshia, which is called the worked examples in the geometry of crystals. Okay, all these problems are taken from Badeshia's work problems in the geometry of crystals. So if you see Badeshia's book, he describes, okay, so here is the reference to Badeshia's book. The transformation strain associated with this martensitic transformation can be represented using the matrix P. Okay, so we have the matrix P, and then we are asked the question, what is the maximum strain experienced by any lattice vector? Okay, we want to say that, okay, any lattice vector you take, the strain cannot be more than this or something like that. Okay, so suppose if the question is asked, this is why we derived the identity. We know that P can be split into R, E, and P transpose P is equal to E squared. So if you can make the E matrix and square of that matrix and the eigenvalues, eigenvectors, that is going to help us solve this problem. So that is the reason why we did all this exercise, why I derived the identity, and here is the matrix, transformation strain matrix that is associated with this particular transformation. Okay, and we are going to answer the question to what is the maximum strain experienced by any vector of the FCC phase when the transformation happens and it goes to the HCP phase. Okay, so how do we do? So to obtain the maximum strain experienced by any lattice vector, we have to look at the eigenvalues of the pure strain component of the transformation matrix. We don't worry about the rotation part because, as I have shown you earlier, rotation always leaves the matrix magnitude unchanged. So if there is going to be any distortion, any contraction or expansion of the vector, that's going to happen because of pure strain. But P transpose P is equal to pure strain squared. So we know the P matrix. So we can take P transpose P, that will be equal to E squared. So if you can calculate the eigenvalues of P transpose P, that will be the eigenvalues of E squared. So eigenvalues of E squared and eigenvalues of E are connected through a square root, and the eigenvectors don't change. Okay. So if we can get the eigenvalues of P transpose P, and if we take the square root, then those will be the eigenvalues of pure strain E. Those eigenvalues will tell how much is the maximum strain experienced by any lattice vector. Okay. So P vector is given. Okay. So let us do this. P is given, right? What is P transpose P? That's what we want to do. So that will be 1 by 12 into 1 by 12. P transpose, so that is 13 1 minus 2, 1 13 minus 2, 1 1 10. That is multiplying P, 13 1 1, 1 13 1 minus 2 plus 2 10. So multiply. Okay. So what do you get? 13 squared and plus 1. Okay. So you can do the other computations in a similar way, and you get the matrix. So what is the matrix that you get? Okay. So you get the matrix like this. Okay. Okay. So you can carry out. So in the other one also 13 into 1 and 1 into 13, that is 26, minus 2 minus 2 4, so 26 plus 4 is 30, and so on. Okay. So this will be minus 20, and 13 plus 1 is 14, so that is minus 6, and the others are basically the same type of combinations. Okay. So the last one is the only one which is different, because these are the same three numbers, and 1 1 10, so you can multiply and get, that is 13 plus 1 14, and minus 20, so that will be minus 6, and so on. Okay. So let's go back to the slides. So you now have given the transformation matrix. You can take the transpose of the transformation matrix, you can multiply the transpose with the matrix, that is equal to the pure strain squared. So this is the matrix you have. Now we want to get the eigenvalues of this matrix, because if I get the eigenvalues of this matrix, then I will be able to say what is the direction, or which lattice vector is going to experience maximum strain. Okay. So how do we do that? Here is how we do this. Okay. To get the eigenvalues, we have to solve what is known as the characteristic polynomial. How is the characteristic polynomial obtained? The characteristic polynomial is obtained if A is your matrix by taking A minus lambda I and taking the determinant of this A minus lambda I. So which is what we are doing. So this is the matrix. I put I is the identity matrix, so it will have only diagonal terms. So minus lambda I means minus lambda on these parts, and take the determinant equated to 0. Okay. So if you do that, okay, you can check the algebra that you get this third order polynomial. So you get lambda cube minus 3.125 lambda square plus 3.125 lambda minus 1 equal to 0. The roots of this polynomial, because it's a third order polynomial, you will have 3 roots. They are the eigenvalues. Okay, so the problem of finding eigenvalues finally boils down to finding zeros of a given polynomial. Okay, so I want to know what are the zeros of this polynomial. Here again, it is very useful if you have a computer and if you can plot this polynomial, for example. I mean, you can just look at where it cuts 0, and then you can, okay, then you can you can get the eigenvalues fairly easily. Okay, but we don't have the luxury of say plotting it, and then all we need to do is to do some algebra to get the eigenvalues. So how do we get the eigenvalues is the question. There are many different methods of basically getting zeros of a polynomial. So there are lots of numerical techniques for finding zeros of a polynomial, which is what we are going to discuss in this module. Okay. So first one is a very simple minded method. So it's known as fixed point iteration. Okay. It's also known as x equal to gx method for finding the roots of a polynomial. So what is this method? How does this method work? Okay. So let's go back and look at this expression. So you have 3.125 lambda. You keep this on the right. Take the rest to the other side. So it is 1 minus lambda cube plus 3.125 lambda squared, and divide everything by 3.125. So 1 by 3.125 plus lambda squared, because this is plus 3.25 lambda squared and 3.125 is what you are dividing, plus minus lambda cube by 3.125. So that is what is written here. So I have rewritten the polynomial as lambda equal to minus lambda cube by 3.125 plus lambda squared plus 1 by 3.125. Okay. So now you keep taking values. For example, first if I take lambda to be 0, what do I get? This is 0, this is 0. I get lambda to be 1 by 3.125. Now I substitute lambda to be 1 by 3.125 here in this equation and get what is the next lambda. So if I keep doing it, okay, these values converge, but it takes very large number of iterations. That is why I am not asking you to do this. So when do we stop the iteration? When the lambda that you have and the new lambda that you calculate, they differ only by 10 power minus 6. If you stop, then you get the solution. So if you do that, you get a solution of 0.70346 after about 195 iterations. Okay. If you start, for example, you can start with 2. Okay, that is 4. This is 8 by 3.125 with a minus sign, and then 1 by 3.125. So that will give you a new lambda, and you can go on and you reach 1.4215 after about 140. Okay. We also know that the trace of a matrix is invariant and it is equal to the sum of eigenvalues. So if you have 2 eigenvalues, okay, what is the trace of this matrix? Can you look at this matrix and tell me what is the trace? Okay. Oh, you have to remember there is a 1 by 144 in the outside the matrix. So it's actually 174 by 144, 174 by 144 and 102 by 144. Okay. So it's not 450, it is 450 by 144. Okay. Somebody has given me 450, but it is not 450. It's 450 by 144. So you know the 3.125. Okay. Okay. So yeah, 150, it's of the order of 150. So 450 by 150 is of the order of 3. So 3.125 is the trace, and you know 2 of them already, 1.4 and 0.7. So that gives you 2.125, right? Okay. So the third eigenvalue should be 1. But you can't get from this particular form of fixed point iteration the value of eigenvalue of 1 unless you use the eigenvalue of 1 itself as the starting point. Of course, if you put 1, then it is 1, and this is a minus 1 by 3.125, and this is plus 1 by 3.125. So this get cancelled. So lambda is equal to 1. So if you use 1, you already get in the very first iteration the lambda value as 1. But you take anything other than 1, you know, very small deviation from 1. You take 0.98, you will still not converge to 1. You will go converge to this. You take 1.01, you will converge to this value. Now this is a problem with fixed point iteration. Okay. So we have found all the eigenvalues of the given matrix. We have used what is known as fixed point iteration. but it has a problem because it converges to two of the values. In this case, we don't have a problem. Third one we could get from the property, namely that trace should add up to all three eigenvalues. So you can add the two eigenvalues you obtained, you subtract from the trace, you will get the third eigenvalue. But this can be a problem. Okay. Now, some of you might think, okay, this is not the only way by which I can write it in the x equal to gx form, right? And you are right. So you can take a look at it. This is not the only way. For example, I could have decided to write lambda cube plus 3.125 lambda minus 1 square root, right, with divided by 3.125. That will be also equal to lambda, right? So there are many different, so I can write it like this. Lambda is equal to square root of lambda minus 1 by 3.125 minus lambda cube by 3.125. No, this is wrong. Okay, so let me write it properly. Let me write it. I think there is an algebraic error there. Okay, so how do we write? So let me take lambda cube minus 3.125 lambda squared plus 3.125 lambda minus 1 equal to 0. I want to write it as equal to lambda equal to g of lambda. So let me take this to the other side. So I get lambda cube plus 3.125 lambda minus 1 equal to 3.25 lambda squared. So let's divide by this. So lambda equal to lambda cube by 3.125 plus lambda minus 1 by 3.125, right? So this is also in the form lambda equal to g lambda. Then you might think that, you know, in this case maybe it converges to, okay, so this is okay except for a negative sign here. I mean, I don't think there is a negative sign. If you see the slide, so I think the expression is okay, but for this negative sign. So you can rewrite the polynomial in this fashion, or you can take the lambda cube term, you keep it on one side, take the rest to the other one and take the cubed root. And if you take this expression, for example, the fixed point iteration of this one will converge to 1 if you start even from 0, okay, but the way it does is very, very interesting. Okay, so this is a pure real calculation, but sometimes the quantity inside this square root will become negative, so the lambda will turn out to be a complex number. So it converges to 1, which is on the real line, but it converges to the complex space. Okay. So this is another thing that you would notice with fixed point iteration. Your solution might lie on the real line, but the iteration will actually take you through the complex space. Okay, then there will be some numbers which is some real plus some I times some number. So it will go through the complex space to get to the solution. So these are problems associated with fixed point iteration, that sometimes it does not converge to a solution, or it converges to a solution which is far away from where, for example, you start with 0 in this iteration, you expect to go to 0.7, but instead it goes to a solution of 1. So it can skip some solution. These kind of things are problematic if you are doing numerically, because a priori you don't know the solution. So you use a method, and then the method, you can't methodically take some intervals and take the values and you try to converge to nearby root values and things like that. So that can cause problems. So there is a method which is known as Newton's method. This is also another point iteration like method, and it converges fast. Okay. So in this method, what we do is that we write it in the form xn plus 1 is equal to xn minus the polynomial divided by the derivative of the polynomial with respect to the quantity. Okay. So let us start with the initial guess of 0. And let's use Newton's method for our polynomial. So what do we get? We want to say xn plus 1 is equal to xn minus all this also are xn cube minus 3.125 xn square plus 3.125 xn minus 1, because that is the polynomial for which we are trying to find the zeros. And if you differentiate it with respect to x, so you will get 3x squared minus 2 into 3.125x and plus 3.125, 1 goes away. So this is the function which we want to iterate. So we take some xn value. So let us take 0 to be the first xn value. What do we get? This is 0, this is 0, this is 0, this is 0, this is minus 1, this is 0, this is 0, this is 2.5. So xn you get as minus 1 by 3.125. Now you can take minus 1 by 3.125 here and try to calculate the next xn value, and you can keep doing it. So this is Newton's method. Okay. So if you do Newton's method, so you get, these are the iterations 1 to 6. So start with 0, then you get minus 1 by 1.325 and so on. So in 7 steps it converges. Okay. So now I want you to see, so let us take this and take an initial guess of 1.1. Okay, I want you to take an initial guess of 1.1 and I want you to tell me what is the xn plus 1 value you get. Okay, so iterate using this formula by taking initial value of x as 1.1. Can you tell me what is the second iteration value? If I take an initial value of 1.1 and use it in this polynomial, what is the x2 I get for that x1? Can you calculate and tell me? It's a very trivial calculation. It is 1.1 minus, substitute 1.1 for x here and 1.1 for x here, and take the number, subtract from 1.1 and tell me that. Okay. Somebody has given me the number 0.99375. So you started at 1.1, you got 0.99375. Of course, you can use 0.99375 and go to the next one and so on and so forth. So if you get, so this is what I have given. If your initial guess is 1.1, you get 0.99375. Okay. And in the next step, if you use 0.99375, you will get to 1 immediately within 2 steps. Okay. If you take initial value of 2, first we will get to, in about 9 iterations, you will get to 1.421. So Newton's method is superior in terms of convergence, but it is known that, in this case it is converging to all the 3 values, but it is also known that Newton's method also has this problem of converging to a root which is far off even when you start close to another root. Okay. So what we want is a numerical method which will surely converge to the value that I am closer. If I am closer to a root, I want to make sure that I converge to that root and to no other root. There is a method which will do this, which is known as the bisection method. Okay. What is the idea in bisection method is very, very simple. So I would like to show that it's a very neat idea. Okay. So what happens in the bisection method is as follows. So what do I have? I have some f of x. Okay. So these are the x values. What is it that I am trying to see? I am trying to see where this polynomial is, where are its zeros? That is, where does the f of x equal to 0, right? So this is point A where f of x equal to 0. This is point B where f of x equal to 0, etc. and so on. So it might have another C at which f of x equal to 0 and so on. So the idea behind bisection method is very simple. Bisection method says that choose a point which is on the positive side choose another point which is on the negative side. Okay, let me call it as A, this is as B. So if you take f of A that is greater than 0 and f of B that is less than 0, so f of A, f of B, if it is less than 0, then you know that your 0 is bracketed. Now you take A plus B by 2, so that point is somewhere here. So that is A plus B by 2. Now you calculate f of A plus B by 2 and f of B, that will be positive. F of A and f of A plus B by 2 will be negative. So that means your root is bracketed between A plus B by 2 and A. Now you take the average of these two. So that will be A plus B by 2 plus A divided by 2, and for that point then you do. So you keep doing this till you converge to the solution. Okay. So let's go back to this slide. The bisection method algorithm which is described in the slide. So if you can bracket the zeros of a polynomial, then bisection method will assure convergence to that root. It will not go to any other root, right? Because you are always between those 2 points, and if your root is in between, it will always go there. So in this method we use the fact that root is a point at which f of x is 0. So above and below if you go, f of x minus delta, f of x plus delta is always negative, where delta is a small number. Okay. Now bisection. So you identify 2 points A, B. So you find out whether the root lies between A and A plus B by 2 or A plus B by 2 and B, and correspondingly you discard half of the interval that you choose. So by choosing to discard half of the interval at every point, then you reach to the root. So and you can decide to what accuracy. So you can keep on refining your interval to get to the actual solution. Okay, so let us take the polynomial lambda cube minus 3.125 lambda squared plus 3.125 lambda minus 1 equal to 0. This is for which we are trying to find out the eigenvalues. Now I'll choose value of A as 0.8 and value of B as 1.1. Okay, and you can identify the root. Okay. Now as compared to Newton's method, for example, there is no derivative function and there is no several evaluations because it said x minus f of x divided by f prime of x. So there were so many computations. In bisection method, there is no such complicated calculations. All you need to do is 0.8 you put here, 1.1 you put here, and then 1.1 plus 0.8 divided by 2, that is 1.9 divided by 2. That is what 0.8 1.9 divided by 2 will be 0.94 or something, 95. So 0.95 you find out, and you find out which two values have the same sign, and the root is bracketed within the other one. So by design it identifies the bracketed root. So unlike fixed point iteration, these iterations do not jump over the root and identify some other root. Okay. So now, so you can use bisection method, but there is a problem. Okay. The problem is as follows. So how do I know where the roots lie so that I can use the bracket, right? If I have plotted the function, then I know where the roots are. But if I don't have that, how do I know where the root is? This is where there is a theorem called Gershgorin's theorem. I don't know if it has been taught to you as part of some linear algebra course, but you will see what is the use of this theorem. Okay. So Gershgorin's theorem says that eigenvalues lie in circles whose centers are at aii with radius equal to the sum of the magnitudes of the other elements in row I. Okay. So what does it mean? So you take this row. So the center of a circle which is at the point 174 by 144, that will be the center of that circle. Using that as the center, if you draw a circle, magnitude of which is 174 by 144 plus 30 by 144 plus 6 by 144. Okay, so that is the radius of the circle. So within that radius, with that as the origin, in that circle there will be one eigenvalue. Second one will be similarly here, and third one will be similarly here. Okay, so can you now look at this and use Gershgonin's theorem and tell where the eigenvalues should be? We know already where the eigenvalues are. One is at 1, one is at 0.7, the other one is at 1.4. Can you see if you get them using Gershgonin's theorem? Can you tell me the origins of all three circles and the radius of the circles that you have to draw about that origin? Okay, so that is the question. Okay, you need to identify the three centers, and they are identified basically by the diagonal points. Okay, and then you need to identify the radii. The radii is basically sum of all these three, but wherever it's negative, so please only take the magnitude. Okay, so it is 174 plus 36 divided by 144, things like that. Okay, what do you see? So in the chat window you can write your centers of the circles and their radii. Where is the center of the first circle and what is its radius? So 0.99375, no, 1.20833 and radius of 1.375, 1.45. Okay, somebody has given centers as 1.208, that is right. The second one should also be 1.208. Okay, so 1.208, and where is the third one? That is 0.70833. Okay, so these centers are correct. Then what is the radius of the circles about these centers? Okay, so for third the center is 0.7 and radius is 0.6. So that means from 0.7 plus or minus 0.6. So that is between 0.1 and 1.3 there is a root, right? Which we know to be true, that is there is a root at 1. Okay. Now where is the first and second radii? Okay, so you see that Gershgonin's theorem can help, but sometimes it gives you the same information. So about 1.208 for example, with a radius somebody has given us 0.25 or something. Okay, 174, it's 180, 210 by 144. Okay, so you can get, for example, you will have the center at 1.208, about which you might get some large number. So about 1.2, about 1.4 radius if you take, then that includes both the roots. That includes the root which is at about 0.7, that also includes the root which is at 1.4. Then there is a problem. Okay, so Gershgonin's theorem can be used, and when you have one of the roots it exactly identifies. So within 0.1 and 1 point something there is a root, but there is also a root at 0.7. Okay, so that 0.7 root is bracketed by the other. So even though Gershgonin's theorem in this sense can tell you the range, it still cannot tell you exactly if there is only one root within that range. Okay, they all lie, they all satisfy this condition, but the condition is slightly more relaxed than what exactly it is. So sometimes you will see more number of roots. In those cases you might get into problems if you try to use bisection, but Gershgonin's theorem gives you an assurance that there is a root. So by taking smaller intervals in this range, then you might be able to bracket the root. Okay, so that is okay. So good. So Gershgonin's theorem can be used. So let's. So if okay, so let's go back to the question with which we started. We wanted to answer what is the maximum strain. Okay. So eigenvalues of the pure matrix that we know is the square roots of the eigenvalues of the P transpose P matrix. So you can take the eigenvalues, you can take the square root. So you get the values 1.19, 1 and 0.8, which means maximum stretching stress is about 20%. Maximum contraction is about 17%. Okay, during the Morton-Setick transformation. So by looking at the eigen strains, you can answer questions like this. Okay, so of course there is a question of maximum strain directions, but I think this will be a good time to stop. Any questions? If you have questions, please raise your hand or type in chat. And that can be questions related to what I did today, but it could also be questions related to what we did in the last class. Okay. There is a small multiple choice question and answer session that we will run on Monday towards the end of the lectures, but which will also help you understand how much you have understood whatever we have been doing. But you have been also giving answers, so most of the times I can see. Okay. So AIT map, I see that you have requested an interaction.
Hello. Hello.
Hello. Yeah.
Sir. Okay. Sir, did we have any advanced package like software package in this?
Yeah. So you can use a MATLAB equivalent called Octave for doing all these computations. Sir? There are tutorials that I have written for using Octave, which is available on NPTEL.
There is any software packages?
So Octave is a free software which is available. But they are in interaction.
Can you please tell me name of the software?
Octave, OCTAVE. Octave is the name of the software.
Sir, is there any software?
Sir, like ANSYS, we want to analysis. Is there any software, sir?
Octave is the name of the software. Have you heard of MATLAB? Have you heard of MATLAB? Okay, so it is MATLAB equivalent.
Yeah, yes, sir. Yes, sir.
It's called Octave, and Octave is used for.
Okay.
Yeah.
Okay.
Yeah. Any other question? Do you have any other question?
Okay. Thank you, sir.
Okay.
Thank you very much.
Thank you. Okay, very good. So if there are no questions, next 10 minutes or so let us spend on the remaining part of value of eigenvectors. Okay, so I don't think we'll be able to do simultaneous equations today, but we will take it up on Monday. Now, it is not sufficient to tell just the eigenvalues. So we have found out that 20% or 17% will be the changes, but we are also interested. By the way, how did I say that maximum stretching is less than 20% and maximum contraction is about 17%? Okay. So that I said by looking at these numbers. 1 means that it is the same. 1.19 means 1 has become 1.19. So 0.19 increase in 1. So that is like less than 20%, 19.2% or something. 0.83 means 1 has reduced. So that is why it is contraction. It's about 17% because 0.838, that is like 0.84, that's about 16%, and that much is the. So it has to, if it increases in length in one dimension, it has to contract because the volume I said remains a constant, right? So that is how I gave this information. But this information alone is not sufficient. In addition to knowing that something increases by 20%, something decreases by 17%, I am also interested in knowing which are those directions. Okay. So the maximum stretching and contraction directions are given by the eigenvectors, and the eigenvectors for E and the P transpose P are the same, only the eigenvalue is different. Okay. So how do we get the eigenvectors? So you take the some arbitrary UVW, you are trying to calculate what the UVW values are. You have the eigenvalues, so you substitute one of the eigenvalues. For example, substitute 1 here, or substitute 0.7 here, or substitute 0.4 here, and solve the resulting set of equations, and that will give you the eigenvector. So automatically solving the eigenvalues basically took us to finding the zeros of polynomials. Once you have found the zeros of the polynomial and found the eigenvalues, you come back, substitute in this equation. Now you are trying to calculate UVW. So it becomes a set of simultaneous equations in 3 unknowns, 3 equations in 3 unknowns, which we can then solve and get the eigenvectors. Okay. So obviously eigenvalues is finding zeros. Eigenvectors leads us to the next problem that we want to discuss, namely solving simultaneous linear equations. Okay. So there is a method called power method. So let us discuss. So we'll come back to simultaneous linear equations. So we will do a session on that. Power method is an iterative method. Okay. It's the disadvantage is that it can only tell you the largest eigenvalue of a given matrix. But advantage is that it will also give you the corresponding eigenvector directly. Okay, so you don't need to solve a separate equation, and it's an iterative procedure. So you take some initial, guess, and then you keep on iterating, and then you end up with the eigenvalue as well as the eigenvector. Okay. So even though it is disadvantageous in this sense that it can only give you the largest eigenvalue, but because it also gives eigenvector, so it's a good method that you can sometimes use. Of course, if you take the inverse of the matrix, then the largest eigenvalue of the inverse matrix is basically the smallest eigenvalue of your current matrix. And if it is a 3 by 3 matrix, anyway, we know that the trace should equal the eigenvalues put together. So that will also give you the third eigenvalue. Of course, eigenvector you still need to determine by solving a simultaneous set of 3 equations. But power method is useful in this sense that it can give you eigenvalue, eigenvector together. So what happens in the power method? What is the algorithm for power method? Okay. So we want to find out the highest eigenvalue and corresponding eigenvector of a matrix A. Okay. What do? We take a random vector U. We say V is equal to A times U. So now we normalize the V by dividing each component by the largest in magnitude and call the normalized V as U. So go back. Okay. So what is the algorithm? So let me again show you. So I am trying to find the eigenvectors and eigenvalues for the matrix A. And power method tells me what is the largest eigenvalue and the corresponding eigenvector for A. How does it do? You take an arbitrary vector U and act A on it, and you will get a V. Okay. What do? We divide each component. So suppose this is a 3 by 3 and this is 3 by 1. So you will get a 3 by 1. So we will then have V1, V2, V3 like that. You find out whichever is the largest number in this, the magnitude wise. So you normalize V by dividing by the largest number of this. So the largest number will obviously divided by largest number will give 1, the rest will be less than 1, and that normalized V, okay, by dividing by the largest number with the largest magnitude, you call it again as U and you go put it back here. So you calculate the next V. Okay. So how long I'm going to keep doing it? I'm going to keep doing it till the change in the normalizing factor becomes negligible. Okay. So then the normalizing factor which you use is the eigenvalue, and the corresponding vector that you get is the eigenvector. So this is the algorithm for the power method. Okay. So that brings us to solving simultaneous linear equations. You can go back and as an exercise you can take the A vector that I have given and try to use the power method and try to find the eigenvectors. But of course we will discuss the simultaneous linear equations problem, which I will do in the next session on Monday. Monday we have a session in the morning. Session goes from 10 in the morning till 12. So in that session we will look at simultaneous linear equations, we will look at optimization problems, and we will look at some simple ordinary differential equation solution. Once we solve all this, then we will look at some multiple choice questions that I have made, just for you to know how much of it you could follow, and that will bring us to the end of these modules. Okay, so I'm going to stop here for today. If you have any questions, I will take, or any clarifications if you have, you can tell me. Otherwise, we will stop the session. Okay. I do see some information about when I'm using the board, that sometimes you are not able to see some things. I will try to keep that in mind when I teach next time. Okay. Okay. So if there are no queries, thank you.